Ladies and gentlemen, it is with great pleasure that I introduce our next speaker, Avi Wigderson. He obtained his bachelor degree from the Technion in 1980 and his PhD from Princeton University in 1983. Among his awards, I would like to mention just the Nevanlinna Prize, which he received in 1994. Avi has many outstanding results in the theory of computing, in graph theory, and in other areas around theoretical computer science. But besides these outstanding results, what I think most important aspect of his mathematical personality is his extremely broad knowledge and his extremely broad view about what is going on. Anytime you have any question about what this or that area is really about, Avi will give you a fantastic description, going to the depth that you would think that maybe only somebody, a special person in that area could give. Avi considers theoretical computer science as a key part of mathematics, with a view which I share. And he has been thinking about and working on some of these extremely difficult questions, many of which can be summarized as a simple dichotomy, like determinism versus non-determinism, or what is the relationship between parallel repetition of an algorithm or protocol versus sequential repetition of an algorithm or protocol, or what is the relationship between a randomized computation, a computation using randomness, versus deterministic computation. It is with great expectation that I am looking forward to this talk, where he will summarize his thoughts on PNP and mathematics from the perspective of computational complexity. So, Avi.
Thank you. Do you hear me? Thank you very much. I've written something like, I exceeded the page length they gave me at the proceedings by a lot, and I've written something like 50-some pages on my thoughts on this very broad subject, and then I had to pick a topic for the talk. I could pick several one-hour lectures from this paper I wrote, and what I decided to do is talk about randomness. So let's see if this works. This is the talk I'll give today. I was going to say that randomness, of course, occupies many thoughts and bodies of mathematics in probability, statistics, ergodic theory, information theory. There are many views of randomness in mathematics, but if you just came to the last talk of Terry, he mentioned randomness and pseudorandomness so much that I don't have to go on. Here is the point of view of randomness, again, from computational complexity, when you are short on time or short on any other resource, and you wonder how powerful this is. Okay, so I'll tell you what we have understood in the last 20 or so years about this question. So that's highlights of the or summary of the talk, I'll have to give you some background in computational complexity, and I'll explain what I mean by efficient algorithms, hard and easy problems, and the P versus NP problem I'll have to mention because it will be essentially related, as Terry speculated in his talk, it will be essentially related to the question of randomness, as we'll see. So then in two parts, first I'll demonstrate the power of randomness in computation with examples from mathematical problems, and then I'll tell you why actually this power may not be what it seems. And this will get us into understanding a definition of randomness, pseudo-randomness, and the relation between computational difficulty and randomness. And then we'll see with time, I want to talk about randomness in other settings, in saving space and in understanding proofs, mathematical proofs. Okay. We are going to study the complexity of computational tasks, and humanity always wanted to do things efficiently. Our time on Earth is bounded, after all. But after Turing gave us the definition of an algorithm, this became the mathematical object. So the computational complexity of problems is a mathematical object of study, and I'll give two examples, famous examples. And I want to use it to demonstrate what I'll call easy or hard. So a very easy problem, which we learn in first grade, second grade, is how to do long multiplication. We want to study it as a function of the length of the data, the length of the numbers, how many digits they have, and if in this algorithm we learn, if they have n digits, the multiplication takes something like n squared steps. So that's what we call an easy problem. It has a polynomial time algorithm. That's P. Here's another problem, which is just the inverse of the first. I give you an integer, you need to find its prime factors. And here we are not doing that well. I mean, the best known algorithm so far is something like exponential in square root the number of digits. It's huge for any large number. And if that was the best we could do, this would be a hard problem. Exponential time algorithms are inefficient. The truth is we don't know whether it's hard or not. What's more interesting here is that the whole world, including all of you who are buying using your credit card on the internet, believe that it's hard because that's what the security of the transactions depend on. But nevertheless, we don't know. That's a great challenge, great problem. Here's another problem, which is probably dear to everybody's heart in this audience. Another computational task is theorem proving. The input to this problem is a mathematical statement of our choice, like the Riemann hypothesis, and some integer n, which is how many pages it will be to write down a proof. And the task is to find a proof for this in any system you want, Zermelo-Frankel or I don't know what, of that length, if one exists. What's the complexity of this problem? I mean, I think everybody here will agree that in general it should be difficult, but we don't know that. However, we do know relations between the complexity of problems. For example, it turns out that if there is a fast algorithm for this problem, there is a fast algorithm for factoring integers. So even though we don't know whether they are easy or hard, we know this implication. And this is a consequence of a very basic theorem of Cook and Levin from the 70s, that this theorem proving problem is a universal problem. It's a complete problem in the class NP, which I won't even define, but it's a large class. And in particular, this problem turns out to be equivalent in complexity to a huge number of other problems from mathematics, from computer science, from other sciences that look sort of unrelated. So it's a very special, of course it's very special for mathematicians, but it turns out to be special in this much broader sense. And so if you want to state the P versus NP problem, one formal way to do it is just asking, is there a polynomial time algorithm for theorem proving? Can a child prove the Riemann hypothesis? And we don't know. We cannot rule it out yet. And of course it captures a much deeper thing. It captures questions about whether we can automate, creativity, at least mathematical creativity, but actually it's much bigger than that. So that's the question we cannot answer, but, we have our beliefs, right? So there are all these problems in NP and even beyond, for which we don't only have a polynomial time algorithm, we don't have anything non-trivial. The obvious exponential time algorithm seems to be the best we can do. So if you ask yourself, is any of this problem hard, requires exponential time by the best algorithm or exponential size by the best hardware circuit, you will be forced to conjecture this, and this is a standing conjecture. Everybody believes that, P is different than NP, and in fact, there are problems in NP like theorem proving that probably requires exponential time. So that's one fundamental question of theoretical computer science. Now let me move to the second fundamental question, which is about the power of randomness. So what I want to demonstrate by a few examples is a set of problems, very natural problems, and they are just examples, there are many more, for each of which we have a very efficient probabilistic algorithm, and for none of which do we have even a sub-exponential algorithm so far. So this will demonstrate the power of randomness. So let me start. There'll be examples from different areas of mathematics. These are very basic, simple to state problems. But before that, let me just define what is a probabilistic algorithm. So a probabilistic algorithm is an algorithm, is a program that is allowed to toss coins or dice. So we assume that we have at our disposal just a perfect uniform distribution, just a collection of independent, unbiased coin tosses, which the algorithm can use for its decisions. And of course, once you allow randomness in your computation, the outcome of your computation becomes a random variable. And the question then is, that you may have errors, so what do you accept as a good algorithm? And we'll accept anything that does the job with very high probability, with, let's say, 99% probability. Why should anyone tolerate error why should anyone tolerate error, period? Well, there are many answers. The good, maybe the best argument is that we tolerate it anyway in life all the time, so why not in algorithms? Actually, errors in probabilistic algorithms are much better behaved than errors in life. You can decrease them arbitrarily, which is something you cannot do if you just cross the street and want to avoid being run over. So you can repeat a probabilistic algorithm many times and decrease the error exponentially. And of course, the real reason we use it is for some problems we can, can't do it deterministically, so we use randomness. And it's a very powerful tool, and here are the examples I want to give. First is number theory, recognizing primes. And here, I've been giving similar talks for like 20 years, and primes were my prime example of a problem that has a probabilistic solution but not a deterministic one, but this was ruined 2 years ago by a beautiful result. So in the 70s, let me say what the problem is. I give you an n-bit or n-digit integer, and I ask you whether it is prime. I refer it to Gauss here. Of course, people asked it, I guess this doesn't matter. People asked it for ages, but Gauss wrote the most explicit paragraph challenging the world with finding the complexity, computational complexity of this problem in the language of his century. He's talking about indefatigable calculator. So it's clear it was after the exact computational complexity of this problem. In the 70s, Strassen gave a probabilistic algorithm that really started the age of probabilistic computation. very efficient algorithm for testing primality, and that used to be the best example, and in a wonderful breakthrough that I'll talk about later too, Agarwal, Kayal, and Saxena found a deterministic algorithm. So this is not an example of the type I wanted, but there is a related one, which is, I just give you n, the number n, and I ask you for an n-bit prime. Well, I mean, probabilistically it's trivial because of the density of primes. You just pick, let's say, 1,000 n integers in the range, in, numbers of n digits, and apply to each of them the primality test. Well, with high probability, one of them or many of them will be prime. So the density guarantees it, but if I ask you for a deterministic algorithm, nobody has an idea how to do it in less than exponential time so far. So that's one example. Let's do an example from algebra. So polynomial identities. Here is one famous one, right? If you take the van der Monde matrix of n variables and look at its determinant, well, we know that it will equal this product of all differences, and van der Monde proved it. But I just want to state, that to clarify, right, this is an exponential size object. If you open it up to check all the coefficients, that all the coefficients are 0, I mean, you would never end. So, of course, that's not the way van der Monde proved it. He found a better proof by induction. That's a simple theorem. But in general, if I gave you another polynomial, something that you think, or if you had one, you came up with one that you believe is an identity, it's a polynomial that's described somehow implicitly, like this one, and you want to know whether it's identically 0, it vanishes completely, how would you do it? Well, again, probabilistically, it's very simple. There's this simple Schwarz-Zippel algorithm. Well, I mean, we know if it's not identically 0, then it's a variety. It has measure 0, so a random point will not be on it. And you can even discretize it. It's enough to pick a value for each of the variables randomly in the range, let's say, between 1 and 100d, any 100d, let's say, integers for each one. You pick it randomly, so you do this very simple sampling. And, well, of course, if your polynomial was identically 0, you will always get 0. But if your polynomial is not identically 0, you will get a non-zero with extremely high probability. That's very simple, and, again, nobody has an idea how to do it deterministically in sub-exponential time. Let me just stress that, of course, you need many values in your field, whatever the field is, for this algorithm to run, and there's a reason. If you're working over very small fields, the problem is can't be complete, so you can't hope to find such an algorithm. But on the other direction, if the field is large enough to contain so many elements, this is the degree of the polynomial, then you can do much more than testing 0. In fact, there are better algorithms, and they are used all over the place in the computer algebra packages. You can factor polynomials, for example. And again, this is a probabilistic algorithm and has no deterministic counterpart. Okay, analysis. I'm trying to touch on everything. So, Fourier coefficient. Suppose you have again, an exponential size object described implicitly, like a function on the cube, on the Boolean cube. Let's say it's given by a formula or a circuit, and some epsilon. And you want to find all the large Fourier coefficients of the function. Okay, so even though there are exponentially many, there aren't too many bigger than epsilon, right, just by Parseval. So, can you do it? Now, in the previous two examples, the probabilistic algorithms themselves were very simple. You just sample blindly and it works. Here it's much more sophisticated, and there is this beautiful probabilistic algorithm of Goldreich and Levin, which does adaptive sampling, and which gets, with high probability, all the large Fourier coefficients. In fact, it can be extended to arbitrary abelian groups, again, of exponential size that are described implicitly. And it has very important applications in coding theory and complexity theory. And again, we have no deterministic way of doing that. And the last one, geometry, is again a very basic problem. The problem is that you are given in very high dimension a convex object, let's say a polytope. It's given implicitly, let's say a polytope given by the bounding hyperplanes. And you want to estimate the volume of this body, like the volume of this audience. Now, I say estimate because it's not hard to see that computing the volume exactly is even worse than NP-complete, so we should settle for an approximation. That was a well-known problem for a long time, and then came this ingenious solution, first by Dyer, Fries, and Cannon, and then by a host of people with more and more refined, beautiful, faster algorithms and similarly beautiful analysis. So let me give you the idea of this probabilistic algorithm, because again, it's very different than the previous ones, just a very highlight. So there are several ideas that come in here. The first thing is you discretize the space, so computing the volume is, approximating the volume is roughly counting the number of, approximately counting the number of lattice points inside this body. And the next is a connection, a very basic connection between approximate counting and uniform sampling. It turns out that it will be sufficient to find an almost random point inside the body to approximately count, but now we cannot throw darts, we cannot sample in a bigger ball because we are in high dimension and the probability of falling in the body is exponentially small. So what you do is something much more clever. You take a random walk inside this body. So this is a slide I stole from Latsi-Lovas. I couldn't have generated that. So you take a random walk inside the body, and if you just happen to move out, you immediately go back. And, well, it's a Markov chain, and, you know, it eventually will get you to a uniform point in the body, but eventually, you know, when? And it turns out to show that it's rapidly mixing, to show that in polynomial time you get to a random point, you have to analyze the spectral gap in this Markov chain, and for this you need to develop either parametric inequalities for general convex bodies, and these are the type of things that go into the proof. I should mention that this type of Markov chains appear a lot. It's the Monte Carlo method in statistical mechanics, but analyzing these various Markov chains borrow from these techniques here, and it's important in group theory and other areas as well. Okay, so we've seen 4 examples, and you should believe me, or you probably know that there are many more. Does randomness help, or these are just, demonstrate our ignorance? Are there problems that have probabilistic polynomial time algorithms but no deterministic counterparts? That's the second fundamental problem in theoretical computer science. And, well, certainly the examples and our current knowledge would tempt you to conjecture that the answer is yes. Let me remind you the previous fundamental problem. Does NP or this set of problems require exponential time, exponential size, and we also believe that. So the main point of this lecture, for those who didn't know it already, is this. These 2 conjectures, first of all, even though they don't look related at all, are intimately related. In fact, one of these conjectures must be false. And if you ask which, it's this one. So, well, what's going on? You know, what is the connection? Where is this coming from? So that's what I want to explain to you in the next couple of slides. So again, what is another way of saying it is, if there are hard problems, then randomness is not as powerful as it seems. So let's go to this. What's the connection between hardness and randomness? So this has evolved over, it's a program really, if you want to give it the mathematical name, even though it was not stated as a program. It's just an evolution of results and understanding starting from the mid-80s, even continuing still today. is that you can take hard problems and construct from them pseudo-randomness that looks good enough to all probabilistic algorithms. You can trade off hardness and randomness. And let me give you one concrete one, which is in some sense the strongest of this set of theorems. I'm not stating it in full generality, but in particular, if any problem in NP requires, exponential size, it's as hard as we think it is, then I was very happy to see this in Terry Tao's slides. Then BPP equals P, which in plain language means that every probabilistic polynomial time algorithm has a deterministic counterpart. There is nothing you can do with randomness that you cannot do without in polynomial time efficiently. This is what I want to sort of sketch the ideas of in a second. I just want to mention that now that we have a connection between hardness and randomness, at least hardness implies pseudo-randomness, you might wonder how tight is this connection. And it turns out that very recently we have been able to start to get partial converses to this theorem. So these two fundamental questions that seem so distant are not only related in one direction, in some sense they are even related in the other direction. And from de-randomization you can sometimes build hard problems, prove lower bounds on complexity. I will not talk about that. I'll just talk about. But you can hear more about this. This subject, both in Luca Trevisan's talk and in Omer Reingold's talk later this week. Okay, so let me go back to this. How do we take hard problems and eliminate randomness? What is the connection? Okay, so the key word is computational pseudo-randomness, very, very, very different than the pseudo-randomness that you've seen in Terry's work. And let me try to explain what do we call pseudo-random. So first let me say, what is our problem? What do we want to do? We want to show that we can take any probabilistic algorithm and remove the randomness and still run it, deterministically somehow. So what is a probabilistic algorithm? It's an object like this. It has an input. It has a source of randomness. And remember, this is perfect randomness, independent unbiased coin tosses. That's why they are gold colored. And then we get our output with high probability is correct. And we want to eliminate randomness. So let's reduce our expectations a little bit. Let's not ask ourselves how to remove it completely, but let's ask ourselves what other distributions would do as good a job as the uniform distribution. Okay? So, what other distributions here, maybe biased, correlated coins, would still cause the same algorithm to behave similarly, to compute with high probability the right answer? And, well, the answer is a definition. It's a fundamental definition. At this point, we'll have to give it meat, but let's call such a distribution pseudo-random if it satisfies exactly what we want. If every algorithm on every input, every efficient algorithm on every input will behave the same. So distribution is pseudo-random if no efficient procedure can distinguish it from random. That's the key definition. And once you have this definition, it's clear that you can replace this by this. The question is whether there is any pseudo-random distribution other than the uniform one, and whether you can, build it without randomness. So that's exactly what we are going to do. We are going to create a pseudo-random distribution without randomness, deterministically. So let me tell you how. Oops. So we have no bits. We want to create these n pseudo-random bits. Well, we can cheat and take let me just stress. This construction should be deterministic and efficient, because we want the whole construction together to be efficient. Okay, so we can cheat and start not from no random bits, but from a few random bits. Why? Because, if we just let ourselves have log n random bits instead of n, this is no problem because we can enumerate all the possibilities. The number of possibilities is still just polynomial in n. So that's okay. And now what we want to do is to convert these log n pure independent bits into n pseudo-random bits in this sense that will fool every possible algorithm. Okay, so this is the problem. How do we do that? And what's the connection to hardness again? So let me give you a sketch. Yeah, this procedure is called the pseudo-random generator. Expanding a few random bits into many pseudo-random bits is a pseudo-random generator. So how do we do that? What I'll show you is just not how to convert k, log n to many, to n random bits. I'll just show you how to just increase the number of bits by 1 and have a pseudo-random distribution. How to go from there, it's like, well, it takes work, but I won't get into it. So let's suppose that this is our only task. We have to generate something that looks random, that looks unpredictable, k plus 1 random bits from k random bits. So, well, I mean, the first k is obvious. We just copy what we have, right? So that's no problem. We have k random bits already. How do we generate the last bit that should look unpredictable to any efficient computation? Well, I mean, there is only one thing we can do. We have just these 3 bits, so we can take some function of them. And this function should be computationally difficult. Computationally difficult means here, computationally difficult in an average sense, right? We not only should not be able to predict this bit exactly from the previous ones or from the input, we should not be able to even guess it better than 50-50 because that's what random means, right? No efficient procedure should be able to guess it better than 50-50. And so what we need is a very strong hardness. We need an average case hardness of a function. And what we have assumed, well, you already see a connection, but what we have assumed is something much weaker. We just assume that some problem is computationally difficult. Maybe it's difficult just on one input, right? And there is a whole work to do here in amplifying, let's say, amplifying the difficulty of a function that may be hard on rare instances into a function that's hard on essentially half the instances, because yes, no question. It's the best you can do, and there's a lot that goes into this part. But the key thing is that you can use a computationally hard function to compute a bit or bits that look random to any efficient procedure. And that's the key to the pseudo-random generator here. So let me just make sure that we understand the whole process, what happened here. The way we deterministically emulate a probabilistic algorithm is to look at this generator we have just constructed and try, if we want to do it deterministically, we don't have this randomness, so we enumerate over all polynomially many possibilities of the seed, evaluate the output, feed it to our algorithm, and take eventually a majority vote. And this will behave exactly or almost exactly as the probabilistic algorithm behaved initially. Now, let me make a point that's extremely important here about this pseudo-randomness paradigm. We wanted to fool or to remove randomness from all possible algorithms, and we could do it under some assumption, under the assumption that we have a difficult problem, let's say in NP. But this paradigm is much broader, is much more powerful. For example, you may want to fool not all algorithms, you may want to fool a particular algorithm. This particular algorithm is analyzing randomness in a particular way. Maybe you can just fool the use of randomness there. And it turns out that you can do it in many specific instances, and some of the highlights are the primality testing algorithm, the deterministic primality testing algorithm of Agarwal, Kyle, and Saxena. It comes from de-randomizing a particular primality test. And it has no assumptions. And similarly, a problem I'll talk about in a second. Okay, so using this pseudo-random generator, which is based on computational difficulty, you can compute a small set of pseudo-random strings, and their average behaves like the average of all random streams. Okay, good. Let me move to the power of randomness in other settings, computational settings. One setting, which is very ancient, problem is the case not when your time is limited, but your memory is limited. Like you come to a new city, you've never been in, let's say, Madrid, you want to get to your hotel, you have no map, and moreover, you have no memory in the sense that you cannot just explore and note down everything you've seen so far. You just can remember basically where you are and what are the names of the streets that you are currently looking at. But that's all. That's what we call log space. It's, what you remember is about log n bits out of this n size graph. It doesn't have to be planar. It's a general graph. Yeah, so what do you do in this case? I don't know what you do, but here's what these guys do. Beautiful paper that tells you that in any graph, any undirected graph, what you should do is just take a random walk. Drink a bit and then start walking. And amazingly, in polynomial time, you will get to your hotel and to any other hotel in the city. It's not trivial because in directed graphs it's not like that. If you have one-way streets, you're dead. But it's a very elegant, very simple solution to this problem. And this problem is not an isolated problem. Again, it's a complete problem for a natural class of computational problems. And it's a probabilistic algorithm. There was a natural question, can you de-randomize it? It's a very different game than what you've seen before. And there's just, again, a breakthrough last year, amazing result of Omer Reingold, again, he will talk in this conference, is that you can replace this random behavior by a deterministic walk that will do exactly the same, will get you to all hotels in the city. And this walk can be computed again in log space. You don't need to remember anything you see. And even more remarkable is this insight that he had in which the pseudorandom generator, if you will, that he's using, that he's building, is based on expander graphs that seem not to be related at all because most cities are not expanders. And he's using it on particular construction of expander graphs that we've done a few years before, using the so-called zigzag product. So it's a beautiful, I encourage you to go to his talk. That's one setting, the setting of space. And here you see a problem, again, where randomness does not seem as powerful as in general, but there are other problems where randomness seems to be, or so far seems to be more powerful than determinism in the case that you have no memory, but not in these cases. The last one I want to talk about, the setting which is again dear to every person in this room, is about proofs. What does randomness do to proofs? So I want to talk about probabilistic proof systems. This is a notion that came up in two very important papers, Goldwasser, Mikhaili, Rakov, and Babai. And to tell you what a probabilistic proof system, let me tell you first what a deterministic proof system is, which is the proof systems you all know. So we are interested in, proofs for some claims, whether, maybe Fermat or the claim that the Riemann hypothesis has a proof in 200 pages. This is a mathematical statement, and we wonder whether it's true or not. And what's the proof system? Well, we in computational complexity abstract all, proof systems in mathematics very simply. Any proof system is defined by its verification procedure. A verification procedure, a verifier, is an algorithm which has to be efficient, and all proof systems in mathematics are efficient. Of course, we expect to be able to verify proofs we read in papers. It takes two parameters, the claim and the argument, and should satisfy the obvious soundness and completeness. If the claim is true, then there should be a convincing argument, right? And that's a good case, in which case we call the claim, we call a theorem, the argument we call a proof, and everybody is happy. And on the other hand, if the claim is false, there should be no argument that convinces this verifier. That's a soundness. So that's a normal proof system. What is a probabilistic proof system? By the way, I should say that notice in this definition, the prover plays a minor, we play a minor role here. And, somebody has to come up with this good argument. Anyway, what's a probabilistic proof system? Well, the completeness is the same as before. We want that if the claim is true, then there is a proof. And what we are giving up in probabilistic proof system, so what becomes probabilistic is the verifier, the verification procedure is allowed to toss coins and allowed to make errors. Okay, we are allowed to make errors in verifying correctness. This should be appalling to mathematicians, and suddenly you may not want it for, real mathematical purposes, but you'll see that there are good purposes for studying it. So, completeness we want always, and we are willing to give up a little bit in the soundness. So, it's possible, but with extremely low probability, that this verifier will be convinced that a wrong claim is true. Okay, so why, where could you use such a definition? I mean, you certainly don't want it you may not want it in a refereeing procedure, even though maybe you do want it in a... Okay, so let me tell you what probabilistic proof systems have that deterministic ones don't have. What are some remarkable properties of probabilistic proof systems? And I'll tell you about two kinds of them, two varieties. One is the probabilistically checkable proofs, the PCPs, which essentially address the question of trivializing the refereeing process, and zero-knowledge proofs, which sort of protect you against plagiarism. So what are these two probabilistic proof systems? So in both of them, I mean, we have the usual setting. We have a particular claim, mathematical statement. We have a prover who has an argument, hopefully a proof, and a verifier who wants to check it. Okay. In probabilistic proof systems, the verifier who wants to verify, that the argument is correct, is allowed to just sample 100 bits from the proof, whether it's, it can be 100 pages, but it reads only, 100 randomly selected bits of the argument and then computes some predicate and decides whether it's true or not. It seems almost ridiculous. I mean, we know that you cannot catch bugs in proofs this way, but the whole point about PCPs is that the proofs will be written in a particular fashion to make it useful. And here's a remarkable result that is about 10 years old by these people. Every proof, every mathematical proof can be converted efficiently into a PCP, into a format which affords this type of verification with extremely high probability. So if it was really practical, I think it would be fair to say that refereeing would be much easier. It's not really a practical result, it's a theoretical result. However, I want to stress that the major application is not to refereeing, but actually for understanding combinatorial optimization and approximation algorithms, or the hardness of approximation problems. And that's a very, very powerful tool, and these last 10 years I've seen an amazing growth in understanding of difficulty of approximation problems based on this tool. Here's the other magic you can do with probabilistic proofs. We have the same setting, but now we are worried about, before the verifier wanted to verify correctness, now it's a concern of the prover. What is the prover worried about? Well, he may be worried that the verifier will read this proof and will publish first. So, what are zero-knowledge proofs? This is a completely ridiculous concept when you first hear of it, because it's a proof which reveals only the correctness of the statement and reveals absolutely nothing about the content of the proof. It's maybe as ridiculous as the previous one, but you saw we saw that the previous one works, so this also works. Here's a theorem. Every proof, again, every mathematical proof can be converted into zero-knowledge format. So if I had a proof of the Riemann hypothesis, if I really did, I could convince you of it without giving you a hint of what's in there, but you will be certain with any high probability you want that it's true. There is a difference between this and the previous theorem. This is assuming one-way functions, cryptography, or let's say that the factoring problem is difficult. And this indeed is a major application area of, it's not for plagiarism, it goes into cryptography big way, big time. It's a major theorem within cryptography and allows all sorts of magical properties of protocols, cryptographic protocols, to take place. So that's another thing. And both of these aspects, zero knowledge and quick verifications, cannot be done if you have deterministic proof systems, if the verifier is just, reading an entire proof given to him. Okay, let me summarize. One thing that is much more general than this talk is that when you are wearing these computational complexity glasses and consider the efficiency of the procedures involved or the efficiency of the players participating in a particular activity or understanding particular concepts, then concepts change their meaning, and actually sometimes they get their correct meanings. And that happens to randomness, to games, to learning, to definition of knowledge, to definition of proofs or definitions of proofs, and much more. And in particular about randomness, what we've seen is that, the definition here is that it's in the eye, or rather in the computational power of the beholder. It's not an absolute term. It depends how much time you have to study your random sequence and try to find patterns in it. Computational hardness can generate good enough randomness, good enough in the sense that good enough for efficient algorithms. And therefore, the seeming power of probabilistic algorithms is probably just not there. In other settings, randomness is powerful, sometimes cannot be eliminated. There are others I didn't talk about, like distributed computing and cryptography itself. That's where its power is showing. But as I said before, even in probabilistic algorithms, it's a paradigm to build deterministic algorithms. Often it's just design your favorite probabilistic algorithm and then de-randomize it and get a deterministic algorithm. So in some settings it's essential, some settings it's not, and some we don't know. Since these results I described depend on hardness, we better find out whether these problems are really hard. We better solve this major, fundamental question number one. Prove lower bounds on the complexity of some natural problems. Can we do it for factoring? Is factoring really difficult? And we really want to know whether, not conjecture, but know that electronic commerce we use today is secure, or else replace it by base it on other functions. Is theorem proving a trivial problem, or is it hard as we believe it is? Is P different than NP? Can creativity be automated? I always have this when I, at the end of a talk like this, or at the end of a conversation with a mathematician about this, they may say, oh, it's interesting, or so forth, but it's not my problem. To do this, to prove this type of result, I have to get into the boring definitions of Turing machines and algorithms and what. How can a mathematician really look into this? It's not a smooth function or, So, my answer is this. There are many ways to phrase the P versus NP problems. All of you can work on it, and you are welcome to it. Here's a concrete one that's particularly appealing to mathematicians. Doesn't mention algorithms, doesn't mention Turing machines. It's a simple relation between two polynomials that are very familiar to all of you. Let's fix a field. Make sure its characteristic is not 2, otherwise it's not interesting. Here are the 2 favorite functions, determinant and permanent. So determinant of a k by k matrix is just what you know, and the permanent is the same function without the sign. Okay? Suppose you want to compute the permanent of an n by n matrix. Here's one way you might want to do it. Never mind why, but here's one way you can go about it. You can try to project it into the determinant. So you can try to embed your n by n matrix into a larger matrix, a k by k matrix, by way of an affine map, and then compute the determinant of the larger matrix. And what you would want is that the determinant of the large matrix will be the permanent of the small one. Okay? So let's call a map good if it does it, if permanent is a composition of the determinant of this affine map. And let's denote k of n, the smallest k for which this can be done. Actually, it's not clear it can be done. But let me give you 2 theorems. First one is that it can be done, and it suffices to have k exponentially big in n. Like 2 to the n, a little bigger than 2 to the n will suffice. That's a result of Valian, who saw this this connection I'm talking about. And it turns out that, there are even lower bounds, and the best one is the recent one by these 2 algebraic geometers, a lower bound of n squared. What do you need to do? You just need to improve the lower bound a little bit. If you improve it to super polynomial, you have proved that p is different than np. So it's a very concrete, clear, algebraic question that, maybe is the right way to address this question. I put it in quotes because, it's not exactly the same, but it turns out that both the determinant and the permanent are complete problems for particular classes of algorithms like P and NP, but slightly different. And if you separate them for finite field, if you prove this lower bound for any finite field, then you essentially prove that P is different than NP. And the problem for infinite fields, for the complex, the rationals, whatever you like, is interesting as well. So any progress is welcome. Thank you.